Okay, here is your Standard of Excellence advanced question. And it's a signed question, similar to the previous one, but this time we're going to do something a little different. We're going to say, here's the sign. It's 20 kilograms. And we're going to say that this angle in here is 60 degrees, and this angle in here is 30 degrees, and we'll call this T1, we'll call this T2, and the question is the same. What is the tension in both wires? Okay, once again, the force of gravity is mg, 20 times 9.81. So same values we had in our last question. The difference between this question and the previous one is on the previous question, we had one of the vectors which was going completely horizontal. And so it was very easy for us. In other words, the other vector was supporting all the weight of the sign. And so it was very easy for us to figure out what that one of the vectors was, what are the components of one of the vectors. In this one, that isn't the case, because what we're going to do is we're going to take each of our vectors, separate it. So this vector here, 30 degrees, T1, and that's all we know, right? We don't know any of these other values. So all we can do in this case is write expressions for the x component and the y component. But those expressions are going to have two unknown variables. So we'll go ahead and do that. We can say that the cosine of 30 equals x over t1, and therefore x equals the cosine 30 times t1. And as we progress through the question, you'll see why it was important for us to solve for x in that case. All right, y is going to be the same. It's going to be the sine of 30 equals y over t1. Therefore, I'm just kind of skipping steps here. Y equals sine 30 t1. All right, so we have expressions, and both of those expressions have t1 in them. Okay, let's do the other vector. The other vector is 60 degrees. 60, and this is T2, and you're probably getting the hang of this now. Hopefully you're getting the hang of this now, and you'll be able to see very easily that cosine and sine. So we end up with this. For the x component here, we end up with x equals the cosine of 60 T1, and y equals the sine of 60, sorry, T2. T2 I meant, T2, oh, rats. T2, sine 60 T2. Okay, now there's one thing that I need to add here, and that is direction. Because in the red one, we have up and to the right. In the purple one, we have up and to the left. In other words, one of these has to have, one of the x components has to have a negative sign. So let's put the negative right here. Sorry, that's a negative attached to that one. All right, just so you distinguish the different directions. And the y are both positive because they're both going up. Okay, so we've got expressions now for all the components. Now we have to decide, what do we do with those? Well, as in the previous question, the net force in both the horizontal and the vertical directions is 0. So let's go with horizontally first, because that's the easiest one. In terms of the horizontal components, we only have two. We have the one over the red, and then we have the one with the purple. So horizontally, from horizontal perspective, F net equals the negative cosine 30 T1 plus cosine 60 T2. Okay, and we know the net force is 0, so this becomes 0 equals, now I'm going to change these numbers right away because people look at this and they get confused and it looks very convoluted. So I'm just going to get my calculator out and go cosine 30 and just get a numerical value, just because I think people will feel generally more comfortable with this. 0.866 T1 plus, and the cosine of 60 is 0.5. 0.5 T2. Okay. Yeah, of course you're saying, oh my gosh, this is getting very complicated. I got a lot of variables and I'm not getting anywhere fast. But now we will, because now we'll write this. We'll do the same thing for the vertical component. The vertical component, and again the F net is 0, but this time for the vertical components, if we look at a diagram here, we have three things. We have three things in play here. We have the vertical components of the purple vector, we have the vertical components of the red vector, and we have this gravity going down. Right, so 2 going up, 1 going down. So the net force equals the sine of 30 T1 plus the sine of 60 T1, T2 rather, plus negative 196.2. Okay, so those are our three vertical components. And yet again, the F net is 0. So actually what I'm going to do, just to save a step, is this 196. I'm just going to slide it, since it's negative, I'm just going to slide it over to this side here. And then sine of 30 is 0.5, 0.5 T1. And sine of 60, you might have guessed, is 0.866 T2. Okay, we're all good. Now, here's where you really have to use your imagination, and hopefully you've had Math 20-1, and then you will see right away how you're going to solve this problem. If you haven't, then it's not an issue, because we're going to show you how to solve it, and then you've got to head start on 20-1. You've got two equations, this one here, and this one here. And in those two equations, you have two variables. And to solve a system of equations, if you have two equations with two different variables, you can solve for both variables. If you have three equations and three variables, you can solve for the variables, right? But if you have two variables and only one equation, then there are an infinite amount of solutions to it. So two equations, two variables, we can solve for it. And what we're going to do for this one, we're going to use substitution. And what we're going to take, let's take the horizontal one, and we're going to solve this one for, let's solve it for T1. And once we've solved it, once we've isolated T1, we're going to substitute that T1 in right here. So let's see how that works. So again, we're going to take this first formula here. 0. Actually, let's make a shortcut. Let's just move this negative over to this side so it becomes positive. 0.866 T1 equals 0.5 T2. We're going to divide both sides by 0.866. 0.866, and then we're going to get this. T1 equals 0.5774 T2. All right, so what have we done here? We've taken one equation with two variables and we've just isolated for one of the variables. It doesn't matter which one you do. Either one will work. Now that we know T1 equals this, we can substitute this in. Let's go with my dramatic yellow. We can substitute it in right there, because T1 equals that. And if we substitute it into this equation right here, then all of a sudden we have one equation with one variable, and that's really easy for us to solve. So let's do that. It's going to be 196.2 equals 0.5. Now, instead of writing T1, I write this 0.5774 T2 plus 0.866 T2. Okay, and again, you might be saying, "Oh, it's looking really complicated." It's just a lot of decimals, but really, that's just like saying 3 equals 5 times 6x plus 9x. It's actually a very simple math equation that you can solve with relative ease. So multiply these two numbers together, then add those. So you get 196.2 equals 0. That times 0.5 equals plus 0.866 equals 1.155 T2. I multiply these two numbers together, and since they have a common variable, T2, I added it to 0.866. Divide both sides by 1.155, and I'm going to get T2 equals 196.2 divided by the answer is 170 newtons. And that is your answer of T2. How do I get T1? Well, T1 is actually easy to find because I've already got an equation right here that has T2 and T1 in it. And so I'm just going to substitute the 170 in. So I'm going to get T1 equals 0.5774 times 170. And that is going to give me times 0.5, 98.1 newtons. And that is it. Those are my two answers right there. Tension 1, tension 2. All right. Yeah, that's the answer to the question. It's interesting, isn't it? Because T2 has significantly more tension in it, right? Because it's at a much steeper angle. So T2 is taking a lot of the weight. It's taking most of the weight of the sign. All right, that is that for an advanced net force problem. I hope you enjoyed it.